Okay, this is the 10-1, 10-2 notes for statistics honors. We're heading in a little bit different direction in this section. We're going to still stay with the concept of means, but instead of having one claim about a mean and then using a sample to determine its validity, now we're going to have two populations. So in this example, basically we're comparing salaries of college professors from public and private institutions. So we clearly have a population for each one of those. So it makes sense that instead of comparing them to some hypothetical mean, instead we're comparing them to each other. So what would be a logical way to do that? Well, we would take a sample from each population. We would compute the mean from each sample, and then we would compare the two means to one another. Believe it or not, that is the gist of how we're going to be running our hypothesis test for the comparison of two means. Specifically, we're going to be looking at the difference of the two means. Okay, logically, if we do have two samples, we obviously know that they must be simple random samples, but another element must be present if we're comparing two populations. Literally, they can have an effect on one another probability-wise, and if you recall, that is the word for that means independent. So this blank here, basically, we must have the random samples be independent of one another. So in previous requirements or assumptions, we would say they need to be random. Now they need to be independent random samples. Okay, but if you recall, before we actually went and talked about confidence intervals and hypothesis testing, which was from Chapter 8 and Chapter 9, we started in Chapter 7 when we talked about sampling distributions. And sampling distributions form the base for a lot of the calculations that you do when doing confidence intervals and hypothesis tests. So now we have to return to the sampling distribution for this scenario, which is the difference of two sample means. So if you look at the formulas for the difference of two sample means, the sampling distribution, they are going to be as follows, this little bracket here. I just want to bring you back to previous sampling distributions that you've learned, specifically for z's in this standpoint. So if you recall, the mean of the sampling distribution was always going to be the mean of the population, and the standard deviation of the sampling distribution was always sigma over root n. Okay, so now what you see over on the left side, these formulas here are going to be the new versions of those. So if we're doing the difference, it makes sense that the mean of the sampling distribution is going to be the difference of the two population means. Makes sense. But then we have a very strange formula here that doesn't look a lot like what you see over here, right? So how do you actually come to this formula? Well, if you go back to what we knew before, we knew that we always had sigma over root n as our distribution. Well, now we actually have two populations. So you'll see over on the left, what's a big thing here? Well, there's subscripts now, right? So mean of 1, mean of 2, you have variance here of 1, variance of 2, sample size, so there's subscripts. So in order to pull this off, we basically need 2 sigma 1 over root n1 and sigma 2 over root n2, right? So this would be the standard deviation of the first sample, first population, and this would be the standard deviation of the second population. So how do we combine them? Well, what's the big thing that students often say? Hopefully you see it here. See this plus sign? So students are usually like why on earth would you actually add these together if you're subtracting the means? Well, hopefully you can kind of make some logic here that if you're combining two samples, no matter whether addition or subtraction, you are going to get more variation involved because there's two things at play. You're never going to decrease the variation even if you subtract them. So no matter whether you add or subtract sample means, you're going to get more variation. So that is why you end up with a plus sign for their sum. But we don't usually add standard deviations directly. So what we did for this standpoint is we square each one of these, which means you're going to get sigma 1 squared over n1 and sigma 2 squared over n2. Then you add them, but then we have to get back to the proper units, which are now squared by taking the square root. So this is the actual formula that you see here, which is over here. So that's where the formula actually comes from. Do you have to know that? Not really, but some students like to see where formulas come from, so that would be where they do come from. But the one thing really to take out of this is if you see these formulas, they are a key component and the subscripts are going to be a little bit different. Also take note that the difference has to be normal, and we will talk about that a little bit later when we do this. One side note, here they talk about how we are not going to be doing anything with z-tests when it comes to the difference between two means. If you recall, when I started z-tests and then I went to t-tests, I noted that z-tests are not very common in the real world because it's how is sigma known if mu isn't when they go hand to hand. So in the textbook, all they do is concentrate on t-tests when it comes to the difference between two, which means we're going to be using S1 and S2 to estimate sigma 1 and sigma 2. Okay, so the first thing we're going to start with here is a unique scenario of a hypothesis test. So we're talking about the inferences for two population means using independent samples, and yes, they'll be random as well. But specifically when standard deviations are equal. Now just note here, this equal isn't exactly the word as we know it. It could be approximately equal. So that means they could be in vicinity of one another in terms of value. They very rarely will you get two distributions that have equal standard deviations, but if they're close, then we use that. And when we do that, we always use what's called a pooled test. Okay, and this will come up a little bit in our in the calculator in a little bit, and I'll explain what that's all about. Okay, so let's talk about the distribution of a pooled t statistic. So essentially, how do we calculate t in this setting? So just as a reminder again, how do we calculate t before? We had, with a one sample scenario, it was x bar minus mu over s divided by root n. Okay, so now you can look at that and then you can look over on the left side and see the formula, and you'll see that they are in the same order. Essentially, we have your x bar scenario on the left, so instead of just x bar, we need the difference of x bar. And instead of mu, we have the difference of the mu's. That makes sense. In the denominator, though, we have something totally different. But if you look at them, the variables are still involved. So we have something over here called S sub p. This is called the pooled standard deviation. We'll talk about that in a second. And then we have the square root of 1 over n1, 1 over n2. So for the rest of this page, I'm basically going to talk about the elements that you're not familiar with, which is the SP, everything in the denominator in reality. So we'll talk about more how to apply this formula in a second, but let's talk about what this is all about. So pooled sample standard deviation. So SP, which is right here in the formula, that's this. So believe it or not, that is this crazy formula right here. So this formula, why do we use it? So instead of dealing with, if we have standard deviations that are really close to one another, instead of taking them completely separately and having they interfere with each other a little bit, so we find like a middle ground of standard deviation, which is going to be almost halfway between them, which will end up being the pooled standard deviation, which we only have to write once, which sort of makes the formula a little bit easier to use. So we will always calculate the pooled standard deviation first because we need it in order to find t. Okay, what is the other part of this? Going this way. So what about that formula on the bottom right here? So if we're looking at, let me get rid of all this. So if we're looking at just this formula, where does it come from? Well, if you remember, if we look back at this formula over here, this formula, specifically the right side, if I was to rewrite that over here, it would be this, right? So this is the sampling distribution of the difference of the sample means. So how can we alter that in order to get this? Well, believe it or not, you can. So how? Well, if the two standard deviations are relatively equal, then we can drop the subscripts completely and just have them both be sigma squared, like you see here. And if they're both sigma squared, we can actually do a little bit of mathematical computation because we can, or algebra, we can actually factor out sigma squared. If we do that, we get 1 over n1 plus 1 over n2, and this is the same as this. Okay, radicals by multiplication can be divided. And then this is actually just equal to sigma, square root of 1 over n1 plus 1 over n2. So the key is if you look at the formulas that we have here, so hold on a second. If you look at the formulas that we have so far, look at this right here, and look at this, they are basically identical, except we use SP in order to estimate sigma in our problem. So that's where the formula actually comes from. They're basically the same thing. It's just a little bit of algebra gets you there. Okay, last thing, which is also super important. Remember, the degrees of freedom was always n minus 1 whenever we had a t-test. Remember, in order to use the t-table, we need the degrees of freedom because each t-curve is different based on the sample size. So now the degrees of freedom is going to come from 2 samples, which means we need double the degrees of freedom in terms of using those formulas. So by double, I don't mean double one of them, because they could essentially be 2 different sample sizes. I know that sounds weird, but they could be. One could be 15 and one could be 18. So how do we do that? We actually add n1 minus 1 plus n2 minus 1 and get n1 plus n2 minus 2. And this is the new degrees of freedom for our pooled t-test that we will be using for both our tests and our intervals, actually. Okay, so let's start with hypothesis testing. So the test that we're going to perform is called a pooled t-test. In the calculator, it is stated as 2SAMP t-test. Okay, and within 2SAMP t-test on your calculator, which is once again is in the stat calculate menu, remember, basically you're going to have the option for whether to choose pooled or not pooled, and of course, you're going to say yes for pooled. I'll get more into the calculator a little bit later, but that's going to be the idea for that. It's a 2-sample t-test, but we are talking about a pooled variety. So let's talk about assumptions. So we've covered these a little bit. So it's got to be a simple random sample. They have to be independent. We need each sample to be normal. Does that mean they originally were normal? Not necessarily. Each one could be greater than or equal to 30, so n1 or n2 could be greater than or equal to 30, and then I'll show it. And then again, for it to be pooled, we need approximately equal population standard deviations. Okay, that's the first part. So assumptions are a little bit different. Next part, this is going to be a change. So your null and alternative hypotheses are now going to be a little different. Not in the way you write them, but in the fact that now that there's 2 samples and populations we're dealing with, believe it or not, we actually are no longer going to have a number. So what do I mean by that? So the old null hypothesis was mu is equal to, we called it mu naught, but in reality, it was just a number. So you've done so many tests so far, you know what I mean. So mu is equal to 400 yards or something like that. So it was a number. Believe it or not, there are no numbers other than subscripts when it comes to null and alternative for 2-sample t-tests or pool t-tests. So the null hypothesis is again going to be a statement of equality, but it's going to state that the population standard deviation or population means for the 2 scenarios are the same. So again, a statement of equality, but the population means are the same. The alternatives are going to be similar. They're going to be not equal to, less than, or greater than, but instead of any number, you're just going to write the mean is not equal to the other mean, or the mean is less than the other mean, and so forth. So it's going to be a little bit different, which we'll cover in the example, but that's going to be the idea. What about the test statistic? Well, believe it or not, something already changed already. So if you go back and look at what we had up here, look at the numerator of this guy right here. See this? Okay, that all of a sudden is changed, so now this is gone for some reason. So let's talk about that. So if we go to our test statistic over here, the numerator was x bar 1 minus x bar 2 minus mu1 minus mu2. So according to this is gone for some reason. Like, what happened to it? It's like magic. It isn't magic. What's actually going on? Well, if you look at the null hypothesis, we have this. Well, what does this imply? This implies that if you subtract mu2 from both sides, you're going to get this. So logically, if two things are equal, what's their difference? It is 0. Make sense, hopefully? So if mu1 minus mu2 is 0, then what happens to this? If this is assumed, it's not part of the scenario, which is why that's not in the formula anymore, and we actually have an easier time of things than just using this. Denominator is the same. Your SP is the same as what we already talked about before. A lot of this we went through. I think all of it, actually. Yeah, we already went through all this with what I just was talking about in terms of observation, so we don't have to go through that again in terms of an explanation. Okay, let's do our first example here. I'm just going to read what it says. So let's return to the problem in the previous section where salaries of professors in thousands from private and public institutions were compared. Suppose independent random samples of 35 faculty members from private institutions and 30 faculties from public are taken. The data is shown below. Okay, so we're given data. We have sample 1, which is private institutions, sample 2, which is public institutions. It says, suppose we are asked at the 5% significance level if the data provides sufficient evidence to conclude that the mean salaries for faculty in public and private, this should say private, that's a typo, private and public institutions differ. Okay, so the key is that we have to run a test now called a pooled t-test that is going to set this. Now, worth noting, we don't know right now that the two standard deviations are the same because we don't have any values. So how do we do that? Well, once again, if we go to the next page here, you can go into your calculator, put this into L1 and then this into L2, and then you can do now 2 var stats in your calculator, which will give you a very long list with appropriate subscripts of all of the realms. So they're going to give you everything: mean, median, standard deviation, by number summary, everything will be there. That'll give you that information. You could also do one variable stats on each one if you wanted to, but that is pretty much what you're gonna end up with if you go through the whole thing and find the values. So I did the values for you here, so you can see them right here with all your. This is, of course, is going to be variable 1 and this is going to be variable 2 by the subscripts that we look at. Okay, so let's start with assumptions. So it says it's stated explicitly in the problem that these are independent random samples. Good. So this takes out the first 2 assumptions right here. So this one and this one. We need these to be normal. Well, it doesn't say anything about normality, but look, we have 35 and 30, which means that we're clear to go and state that these are normal. So the only thing that is left to do is determine if the standard deviations are approximately equal. So here's your first chance at this. So if you look at this, these 2 standard deviations right here, 26.21 and 23.95. So these are, in statistical thought processes, similar. Okay, they are not equal, but they are close enough where we can do this. When they mean by not equal, they are significantly different. These are close enough for us to say, okay, we can now use equal standard deviation process called a pooled t-test. And that's what we're going to actually continue with when we're doing the problem. So let's start with a pooled t-test, and how do we do so? So null and alternative. So the null hypothesis is a statement of equality, and it's, believe it or not, always the same. It never changes because there's no numbers involved. So it's always stating that the means, population means are the same. So mu1 is equal to mu2. Small note, by the way, there you can also do subscripts to replace the 1 and the 2. When I actually learned this a long time ago in my schooling, I would put subscripts there like mu priv is equal to mu, pub or something like that. Or if the variables were different, I would just put the first letter there. You can do that as well. I'm not going to stop you from doing that, but the book doesn't do that ever, so I stick to just using 1 and 2, so I'm consistent with what the book is going to do. So what is the alternative? The alternative is either going to be mu1 is less than, mu1 is greater than, or mu1 is not equal to mu2. So let's look at our problem and see where the key word is. Well, first things first, if you look at the means themselves, it appears that 1 is significantly larger than 2, 98 and 83. So maybe you might be inclined to say that this is a greater than test, but you guys are good at these things by now to look for keywords, and hopefully this word is popping off the page at you. So we're looking for not equal to as the alternative hypothesis. So again, no numbers, just comparing two means to one another. Okay, so we need the test statistic. Remember, the test statistic requires that we first calculate what's called the pooled standard deviation. This is a very crazy formula, which I'm going to write just for practice purposes once. So we're going to be doing n1 minus 1 times s1 squared. That is actually the variance of the first sample, plus sample size 2 minus 1 times the variance of the second sample, all over n1 plus n2 minus 2. Now note, n1 plus n2 minus 2 is the degrees of freedom. Okay, all we have to do now is take the values that are up here that we would have calculated, and we have to sub it into the formula, believe it or not. So if we do that, we're going to get 35 first sample size minus 1 times 26.21, our first standard deviation squared, which would produce the variance. Then we do the second sample stuff, 30 minus 1 times 23.95 squared, all over 35 plus 30 minus 2. If we do this calculation, we are going to get approximately 25.19. You can take that to more decimal places if you want, which would produce less error. I'm just sticking with the 2 decimal place concept that's going on in my data up here. Okay, once we have that, we can then calculate the test statistic t, which is x bar 1 minus x bar 2 over s sub p, pooled standard deviation, square root 1 n1 plus 1 over n2. Okay, again, we just substitute in the values that we have here. What are those values? It's going to be 98.19 minus 83.18 over 25.19 square root of 1 over 35 plus 1 over 30. This calculation will lead you to approximately 2.395. It could also be 2.40. I just added that in there just to get a little bit more accuracy out of this. Okay, so 2.395 is our goal, our test statistic t, which is what we were trying to find. Now take note, what's really cool about this is, other than the fact that the degrees of freedom is different, once we get to the next step, which is the critical value or the p-value approach, everything is now identical to all the other tests that you did, which means you don't have to learn anything new. The test procedures are identical, which means this is just about using your t in order to find the important information. So if you turn to the next page here, we basically have 2 different methods for doing so. So why not? It's practice. Why not do both methods for now? You won't usually be asked for it. You do need to know how to use both of them, but why don't we take a look at it and see if we can get through doing both methods, and it'll be great review. Okay, so first things first, what about the critical value method? So if you remember, for the critical value method, we would take alpha, which is 0.05, and we would determine whether we need alpha over 2 or not. Well, we need, for our critical values, since this is a two-tailed test, they're going to be plus or minus t alpha over 2, which means we do need alpha over 2, which is 0.025. What else do we need? We need the degrees of freedom. Degrees of freedom is n1 plus n2 minus 2, which is going to be 35 plus 30 minus 2, which is going to be 63. Okay, these are going to be the key components to what we're doing. So now what do we have to do? We have a two-tailed test, so we have to set our boundaries, right? So this is going to be negative t sub 0.025 at 63 degrees of freedom. And this is going to be positive t sub 0.025 at 63 degrees of freedom. So again, we can go into our t table right now, right? And if you look at t sub 0.025 and 63 degrees of freedom, you end up at 1.998 for our critical value. So negative 1.998 and positive 1.998. So what's the only thing left? We have to go back and look at our test statistics. So right here, this is our 2.395. We want to place it where it belongs chronologically. And clearly, this is in what region? Well, in the tails, we have reject, and in the non-tails, we have do not reject. So this is clearly in the rejection region. So our final decision is to reject H naught. Okay, so just a note on our rejection. What does that mean? Well, let's go back to our null and alternative. So remember that our null, which is right here, was that the salaries for the private and public institutions are the same. We rejected that, so therefore we're going with the alternative that they are different. So that is going to be our key, result from doing that the salaries from the two institutions are different. Okay, so last thing, p-value. So we could sit here and do p-value intervals using the t-table, but at this point, I think you guys should be experts at doing p-value using TCDF. So just to point this out from a picture point of view, right now our t-value is 2.395. So this is a two-tailed test, which means not only do we have area over here, but we have area over here, which is from negative 2.395 to the left. So how do we find that? We find this area and double it. So P is equal to 2 times TCDF of, let's go with our primary T on the right side, which would be 2.395 to 1E99. Remember, E is not the letter E, it's this symbol on your calculator, which I believe is above the comma. And then degrees of freedom is 63. Okay, we do this gigantic calculation, we get 0.0196. Remember, we are comparing 0.0196 to our alpha, which is 0.05. Since it's less, then again, we reject H naught. Okay, so same conclusion both ways, but two different methods. But this, basically, you need to become experts in these two methods for determining a decision for our test, because you want to be able to go back and forth and be able to do either. I will be asking you about either on the exam, so make sure you can do that. Okay, real quick, let's just return to the calculator stuff. So you'll see this was our scenario here where we had some data up top here, which was our samples that we dealt with. So our data is here. And then we put this in the calculator to find our stats, basically. We didn't, but it was provided to you. So when you do a 2-SAMP t-test in the calculator, as I said, you'll have the option of pooled yes or no. You're going to choose yes for this test. But you'll have, again, the option of data or stats. Okay, rarely are you given both of these, so the best thing to do is just go with whatever is given. So let's say you weren't given the stats at the bottom here, you're just given the data, then you would enter L1 for one list and L2 for the other sample, and then yes, pooled, and then it will do the whole thing for you, give you your p-value and test statistic. If you weren't given the data, then you would choose stats, and you would enter all of this information into the 2-SAMP t-test. Choose yes for pooled, and then you can verify all of your results. One small thing, in some of these tests, when they get very complicated like this with so many values, some of the t's and the p-values will be a slightly different, a hair different, only because there's going to be rounding involved, so just be aware of that. Okay, let's do one more example just to get this straightened out, and then we'll move on to intervals. So it says, in a packing plan, a machine packs cartons with jars. It's supposed that a new machine will pack faster on average than the machine currently used. To test that hypothesis, the times it takes each machine to pack 10 cartons are recorded. The independent, it should say random results, that's a typo or an omission, in seconds are shown in the following table. Assume the distributions are normal. Okay, so before we get started with anything, so we have a new machine and an old machine. These are the times it takes to pack the cartons. So we're going to say the new machine is 1, old machine is 2 for what we're doing. So before we do assumptions, I want to talk about the null. So remember, the null is a statement of equality, so it never changes. And then the alternative, we basically have the same two values, but we want to determine what if it's not equal to, less than, or greater than. This is tricky. Why? It says, do the data provide sufficient evidence to conclude, on average, that the new machine packs faster? Okay, so a lot of students, when they see faster, they're going to think greater than. Be careful, because faster means less time. If you take a peek at the times in the new machine over in variable 1, they are all somewhat, not all, but they are as a whole a little bit less than the old machine, which means that we are testing to see if the times are less, because that means to pack faster, just to be clear. Now, assumptions. We definitely need independent random samples, so this was a omission that I just saw here. So it has to say random, so independent random results, so we're good there. We need the distributions to be normal. Now note, that's important right now, because if you look at the sample sizes here, N1 is 10, and N2 is also 10. So that's not so good. So normality would need to be mentioned. If normal wasn't mentioned, you would have had to have shown histograms or normal probability plots for each of the data sets. So be aware of that. Lastly, standard deviations equal. Well, we don't know what the standard deviations are. So how do we do it? Again, you want to put this in L1, this in L2, and do 2 var stats. If you do that, I'll give you the calculation. So x bar 1 is 42.14, and standard deviation 1 is 0.683. Over here, we have x bar 2, which is going to be 43.23, and standard deviation 2 is 0.750. Okay, if you look at the two standard deviations, 0.683, 0.7050, they're pretty damn close. So we're going to say that they're equal, which means we are going to use a pooled test. In the next section, we'll talk about tests that are not pooled. Okay, so where do we proceed from there? So we have our null and alternative hypothesis, so then we go to our test statistics. So remember, we need to calculate pooled standard deviation first. So I'm not going to write out the formula this time. We're going to get right into it. We do the first sample size, which is 10 minus 1, times the first standard deviation squared, which is in turn the variance. We add the second sample, which is the same size, minus 1, times the second standard deviation squared, all over sample 1 plus sample 2 size minus 2. If we do that calculation, we are going to get approximately 0.717. Okay, so what do we do with that? Now we need the test statistic. So the test statistic is equal to x bar 1, which is 42.14, minus x bar 2, 43.23, over our pooled standard deviation, which is right here, times 1 over each sample size, the sum of 1 over each sample size. We get that. So what do we get? We get negative 3.40 as a result. So all of that to get this important test statistic. So again, what would happen? You would have the option of either they tell you you need to use one approach, or if they don't, you can just go with it. Now, I'm always really good with the p-value method because the CDF commands in the calculator are tremendous. And as long as you understand them, you can fly through them. So that's where I'm going to go with here. Note, remember, we need the degrees of freedom in order to do that. So the degrees of freedom in this scenario is 10 plus 10 minus 2, which is going to give us 18. So do the p-value. This is a one-tailed test, so we're dealing with a distribution where we have negative 3.40 as our t, and the p-value is in the tail, but only one tail. So we need to work that out. So we're going to get TCDF. We're going to come all the way from a really small value out here to negative 3.40, 18 degrees of freedom, and we were going to get 0.0016 as our p-value, which means we compare that to our alpha, which is right here, and since it's significantly less, we can then reject H naught. So what does that mean if we go over to our null and alternative over here? Our null was basically saying that the new and the old machine are not any different, right? So the new and the old machine over here are not different, whereas they're the same time for packing. Well, we rejected that, and we are now stating that the new machine definitely packs faster than the old machine. So this is understanding what you actually say there is important. So remember, the summary statements for these are the same. So we would have said reject H naught, which means it gives evidence, it does give evidence that blah, 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 and then all you would do is reword the alternative hypothesis that the mean machine time is less than the old machine time. Or you could just say packs faster, right? So either way, this is all the same stuff, but that is actually what you would get in that type of test. Okay, so last thing here, we want to talk about a pooled t interval. So in your calculator, when you're trying to do the commands for this, you're going to do, as usual, go to stat and then tests. So you're going to head over to 2samp tint, 2samp tint. Okay, and you'll have the same requirements that you would have for the test, obviously without the hypotheses. So a pooled t-interval, same idea, right? So you have simple random samples, you have independent samples, they're normal, and you have equivalent standard deviations or approximately. You have two populations, you want to compare their difference with an interval. That's the idea. So we again have the degrees of freedom as n1 plus n2 minus 2. So now let's take a peek at the formula. Okay, things are appearing from nowhere. So if you look at this, we got the formula we need. So just as a reminder, for a one sample t interval, this was the formula. So it was x bar plus or minus t alpha over 2 s over root n. Okay, so again, we look over at our new formula. X bar now becomes the difference of the x bars. T alpha over 2 doesn't change, so that's fantastic. And s over root n becomes basically the denominator of our test statistic, the identical denominator. So all of this is very doable stuff, but it shows you that it's in the same form. It's just a little bit different in terms of the values. So let's now take a look at all of this stuff, right, in an actual example. So if we're going to do, this says return to the professor's salary problem. So I'll show you. I brought this down for us. Obtain a 95% confidence interval for the difference mu1 minus mu2 between the mean salaries. So normally an interval gives us just a range of numbers for a specific one value. Now it's going to be a range of numbers for the possible difference between the values. So just as a reminder, again, when we do confidence intervals, we always start with the confidence level, which is 0.95, and we go to alpha, which is always going to be 1 minus that, which is 0.05. Now, we're dealing with critical values, alpha over 2 values, so that means alpha over 2 is, again, 0.025. Last thing, we also need to know the degrees of freedom. We have calculated this, but we'll do it again. 35 plus 30 minus 2 is 63. Okay, so we have all the information we need. Now let's do the formula. So I'll write it out. So x bar 1 minus x bar 2. I usually do parentheses to keep it away from the other calculations. We want to do t sub alpha over 2. Well, we already know alpha over 2 is 0.025, and we need to multiply by the pooled standard deviation root the sum of the two 1 over the 2 sample sizes. Okay, so all we have to do is sub in the values for this. So we have 98.19 minus 83.18 to start, plus or minus t.025 at degrees of freedom 63 is the same 1.998 we calculated in our test for that, if you recall. Do you remember here? So that is the same value that ends up going here for our interval. S sub p, let's not do that again. So we calculated S sub p right here, right? This calculation, and we ended up with 25.19. You would have to do that out if it wasn't, done, but 25.19, okay? And then the square root of 1 over the 2, the sum of 1 over 2 sample sizes. If we do that, we're going to get 15.01 plus or minus 12.52, which is going to give us an interval of 2.49 to 27.53. Now note, this is the interval in, are you ready? This is the interval in thousands, which means the true interval is not this, it's actually this. $2,490 to $27,530. So this is the estimate for the true mean difference between the salaries. That seems like a pretty wide difference, actually, between salaries. So why don't we just do a quick summary interval, because they asked you to interpret the interval. It's a reminder of what this would look like. So in green, we are 95% confident that the true difference between the mean salaries is between $2,409 and $27,530. Okay, so that would be your summary. So note, we're not estimating a true mean value, we're estimating a true mean difference. Obviously, I could have made this much larger, right? I could have said, difference between the mean salaries of private and public institutions, but for me, this is good enough so that you have an idea of what you're supposed to be doing. As always, you're asked to interpret things quite often, so be aware of that. Okay, so the last concept here is very important. It will become very important as we go. So it turns out that we can actually use some confidence intervals to make a judgment about a hypothesis test. So think about that for a second. So, it kind of makes sense, because if you look at this number 1.998, we're actually using the same value we're using as like a decision-making process. So it actually works out pretty well that we can do that. Now, here's the key though. We can only do that in a scenario where the confidence level of the actual test, or the confidence level of the confidence interval, is 1 minus the significance level of a two-tailed test. So what do I mean by that? If we go to the two-tailed test that we ran for the private and public institutions here, we did it at 5%. We knew that it was two-tailed, right? If it's two-tailed and we have an alpha, which is, in this case, like I said, 5%, right? Right here, two-tailed, 5%. We can then use a 1 minus alpha confidence interval to make a judgment about the test. So 1 minus alpha is 1 minus 0.05, which is clearly 95. And we do indeed have a 95% confidence interval that we're using. So if this was a 90% confidence interval, we could not have used it to make that interpretation. Alpha would have had to have been 10%. Just like if I used a 99% interval, then alpha would have to be 1% in a two-tailed test to make this judgment. That comparison is very important, so make sure you have that in your Okay, the other part about this is actually the top part here. So what is the logic? It says a very interesting observation to make here is that there is a clear relationship between the interval of our previous test in terms of our decision. Note that the null hypothesis was mu1 equals mu2, or equivalently, mu1 minus mu2 is 0, which implies the difference of the population means is 0. Okay, so this is the null right here, right? So if you look at this, this is the null. So as this is the null technically, but this is the same thing over here. So if the null is stating that the difference between the means is 0, if we go to our 1 minus alpha confidence interval and we look at this, note what number is not in this interval. 0. If 0 is not in that interval, then we can right away go, well, that's not a very likely number for a true interval here, for the true difference. So if this is not a possibility, what do? We reject it, and we go to the alternative. Believe it or not, that is it. We can use, because this is an alpha 1 minus alpha situation between a significance level of a two-tailed test and the confidence interval, we can actually make the judgment that we can reject the null just based on this interval. Pretty clever. We're going to do that a lot more in coming sections, but this is a great introduction for you for that.